Welcome back everyone to another video. In today's video we'll be talking about inverse functions. So if you're ready, let's get to it. Okay, so by the end of this video we will learn how to represent inverse functions on a graph, how to figure out inverse functions by doing some algebra, and we're going to spend a little bit of time on trigonometric inverses. Now up on my screen you'll see that we have the function f of x equals x squared plotted. And along with that, you see this blue line here, which is y equals x. Now, on a graph, all inverse functions will be reflected across this y equals x graph. So that means that if we want to find the inverse of f of x equals x squared, then that would be reflected across this y equals x. And I'll show you what it looks like. This here is what the inverse of f of x equals x squared looks like. So as you can see that if you were to think about it, if you were to think about the original f of x equals x squared, which is green, if you were to kind of reflect it over y equals x, then it would come out looking like this. So it's not quite like a 90-degree rotation or anything, which you might think of, because this is going upwards while this is going to the right, but it's more of a reflection more accurately. And let's just do this once more, but with f of x equals x cubed. So I'll show that on screen now. Now this here is more or less the graph of x cubed, omitting all the minor mistakes in my drawing. So the green one represents the original function, while the yellow represents the inverse function. And again, you see that it's not quite 90 degrees rotated, it's just reflected across y equals x. So if you were to look at it tilted, it would form a kind, there would be a symmetry, right? Because that's the point of being reflected, it will form a symmetry. And so you can do this with any function, and when you do it, you'll again get something that's reflected across y equals x when you graph it. Now let's actually figure out what equation is this, okay? We're going to look at it algebraically now, so let's get to it. Okay, so let's start with the first example I gave, f of x equals x squared. Now the first step you want to do is replace the f of x with a y. So we'll write down now y equals x squared. Next, what you want to do is you want to switch the y and the x. So now we have x equals y squared, okay, like that. And finally, you want to solve for y. So, and this is pretty simple in this case, you just take the square root of y. So in the end, we get y equals the square root of x. And we can just replace y with an f of x. So we can get back the original function. Not the original function, the inverse function, but with f of x this time. And you'll notice something, that if you were to graph f of x equals the square root of x, it does not look exactly like the inverse of x squared that I showed you in the beginning. That's because there's a minor mistake, and let me show you what I mean. Now in this example, we see that the inverse of f of x, which is denoted with the yellow graph here, it looks like a parabola, except sideways. But when we were algebraically figuring out the inverse, we got f of x equals the square root of x. And if you look at the graph of square root of x, it's only the positive portion here that's on the positive y-axis and x-axis side. So this one I'm coloring in with blue. F of x equals the square root of x is only that. But then you might say, what about this bottom part here? Even though we did everything correctly graphically, it still doesn't show up when we do it algebraically. And that's because we did not do one thing. Instead of it being f of x equals the square root of x, it would be f of x equals plus or minus the square root of x. Because if you remember, when you take a negative and you square it, you still get a positive answer. And if you take a positive answer and you square it, you still get a positive answer. So that's why, in this case, we're not taking the positive root of it. We're taking all possible roots of it, which is plus or minus in this case. So if you can put this in Desmos or any other graphing calculator, and if you put positive square root of x, you'll get just the top part. But if you put the negative square root of x, then you'll get the bottom part as well. And now let's do it once more, but with f of x equals x cubed this time. This here is f of x equals x cubed. Now, again, we're going to follow the same routine. We're going to first of all substitute f of x with y. So now we have y equals, that's a equal sign, equals x cubed. Now you replace y and x with each other. So now you get x equals y cubed. And finally, you solve for y. So in the end, we get y equals the cube root of x, so cube root. And you can just replace y with the original f of x, and there's your answer, boom. And also, in the case of the cube root of x, you do not need the plus or minus, because in this case, the domain is not restricted, as it was with the square root of x. And one thing to note about these inverse functions is that if you were to compose them, then they should equal the variable itself, x, in this case. So for example, if you have f of x equal x squared, and we already proved that the inverse of f of x was the square root of x plus or minus the square root of x, then if you were to compose them, meaning that you were to put one function inside of the other, so it doesn't matter if it's f of x inside f of the inverse or the inverse inside the original, but in this case, let's say it's the inverse inside the original, like that, then when you do it, you will get plus or minus the square root of x squared. Okay? Now, when you take the square of a square root, they cancel each other out. So this cancels out, and you just have x. And this will always happen if the inverse and if the inverse is the correct inverse of the original. So this is a way to kind of prove that yes, this inverse is indeed the inverse of this function and not the inverse of some other function. Okay? Now, one thing to note here is that when we're looking at the function on a graph, the inverse will have its domain and range values swapped from the original. What that means is that if there's a point on the original, let's say there's a point called AB, okay? Then when we reflect it over to the x-axis, the points that will correspond on the inverse will become, I'm just eyeballing it here, but if you were to just reflect it over, then this point here would be BA. Okay, they switch. Why? Because reflecting it over y equals x. And this is true for all values across its domain and range. And finally, to end this off, I just want to talk a little bit about trigonometric inverses. Now, I already have a video that covers trigonometric inverses, but we're just going to do a little bit of a nutshell video of it in this video. So the inverse of sine of x, the inverse of it, if this is, if that's just f of x, then its inverse would be sine inverse, okay? Now, what does this mean, okay? Now, in the context of trigonometry, when you have the original function up here, whatever x value you put in, now x can either be a degree or a radian, okay? You're measuring some angle, some theta, okay? Then what it's going to spit out is some ratio, if you're thinking in terms of triangles, or a point on the unit circle, if you're thinking in terms of the unit circle. Now, what the inverse means is that instead of putting in a degree or a radian, some angle measure, we are instead going to put in a ratio or some point on the unit circle, and this sine inverse is going to spit out some angle measure, whether that be in degrees or radians. Okay? So for instance, if I have sine of 90 degrees, okay? Sine of 90 degrees is just 1. One sec. Just 1. Okay? Now if I were to do sine inverse of 1, then you would get out 90 degrees or pi over 2, depending on whether you're looking at degrees or radians. Okay? So that's, and this works true for cosine and tangent and cosecant and secant and cotangent. Yeah, right. Okay, so there's a video on all this which you can look at in a bit more depth, but for now this is just the snapshot of it. Okay, that is great. Alright guys, that's the end of this video. If you enjoyed, make sure to subscribe, leave a like, and comment down anything you might like, any questions you might have, or any suggestions for me.